Hello, everyone. Thanks for participating. I am Sina Sajidi. I am a PhD candidate here in the Network and Equality group at the Complexity Science Hub. I have the pleasure of hosting Pourya. Yeah, he is doing his PhD in INSERM Paris. And I think this is in particular an interesting talk because it's a focus on diversity and inequality, but in terms of spreading dynamics. So usually in our group, we mostly focus on structure. This is a specifically different one on the disease spreadings. So I would like to hand it over to Pourya. Thank you very much.
Thank you, Sina, for your kind introduction. This is my pleasure to be here and present my recent work at CSH. Today, I'm going to talk about how network heterogeneity shapes the spatial diversity in pathogen ecology. But to start, I'm going to give you a quick introduction into what are different types of heterogeneity when it comes to spreading disease. Well, in general, we can heterogeneity can be categorized into three types relative to spreading disease. First, biological heterogeneity, contact heterogeneity, and heterogeneity in response to epidemics. Yeah, biological heterogeneity refers to variation in biological response of host to a specific infectious pathogen. For example, in a population, individuals may exhibit different level of susceptibilities, infectiousness, or infection duration. Contact heterogeneity is another type of heterogeneity that we can face, and it is involved heterogeneity in individuals' contact pattern. At a higher level, we identified that, for example, there is age-stratified contact pattern, or in another studies, they identified that there is a social segregation which can be based on ethnicity or socioeconomic status of individuals. And these social mixing patterns, there are tons of studies that arguing that these kind of mixing pattern can affect the spreading of disease. At a more granular state, we can talk about heterogeneity at a level of network structure, contact network. So this is the main topic that I'm going to present, and I will come back to this shortly. So let me just finish this part. The third part of heterogeneity is the variation in behavioral variation in human when it comes to respond to epidemic situation. For example, social distancing and the acceptation of vaccination or other kind of behavioral variation that individual can exhibit. And again, a lot of studies has identified that these behavioral variation could themselves be affected by other factors, such as the severity of pandemic waves or socioeconomic states of individuals. In a collaboration with, in another study in collaboration with Fariba and Sina, we investigated the combination of social segregation and individual adherence to quarantine in a pandemic situation. So in that work, we assume that individuals' ability to adhere quarantine depends on their socioeconomic states. Well, these are the mainly three types of heterogeneity that one can possibly consider. But let's move on to contact heterogeneity. Contact heterogeneity refers to a structure that the number of contact individual had are disproportionately distributed. So this means that some contacts have high activity and higher number of contacts, while other individuals have low number of contacts. So extensive research has been done in this field, and most of them, the central finding in most of this research about heterogeneity, the effect of heterogeneity on spreading a single disease, is that heterogeneity lowers the critical threshold, so facilitate the spreading of a single disease. But when it comes to interacting pathogens, interacting two variants of a pathogen, the situation even gets more complicated. Again, many studies have addressed that the contact network structure can potentially affect the co-circulation and emergence of a new variant. I'm going to just give you a few examples of these studies. For example, we know that in general, when a new variant emerges, there are two possibilities. The new variant may have increased transmissibility or immunity evasion. Well, Carrer and Newman, they first consider that a situation with two variants competing on a network structure, and they assume that these two variants have perfect immunity. So with these assumptions, they identify the epidemic threshold and the epidemic threshold of different possible phases, like the dominance of one variant over the other or the coexistent phases. In another study, Gonzalo and Mayer, they consider this time the partial immunity. And again, they identify the critical threshold and the epidemic size of the second variant. Well, the evolution and emergence of a new variant has also been studied. So in another study, the co-authors indicate that heterogeneity in contact network can lower the evolution and the speed of evolution and adaptation of a new variant. So these studies were mostly about the critical threshold or epidemic size or the emergence of a new variant. But let's consider a situation where the new variant has already emerged and it is co-circulating and interacting with another variant. This situation is actually mirror what we observed during COVID-19 pandemic. During COVID-19 pandemic, we observed the emergence of several variants. For example, here I illustrated the emergence of Alpha, Delta, and Omicron. And you can see that, for example, Omicron variant can emerge and get dominant, while other variants may eventually may lost their domination and eventually phase out. So interestingly, we observed that the outcome of this competition, specifically the growth rate of different variants, is diverse in different geographical location. This means that for a given variant, even for a given variant, we have observed a different growth rate and diverse advantage across different regions. So that's triggered this question that what are the possible key factors that can affect the advantage and the growth rate of a competing variant. But before that, let me precisely and quantitatively determine what is the advantage of a virus and how we can compute it. Well, selection coefficient is a proper indicator designed to quantify the advantage of a virus, of a variant over another. So basically, it is the time derivative of the logarithm of the relative incidence. It can be a positive number or negative. Positive means that the new variant will grow faster than the resident variant and can replace the resident variant. The more positive value means that this replacement happens quicker and easier. With a little math, we can come up with this nice equation. This is P is here the frequency of new variant, and it has a logistic form. This equation enables us to actually provide us with a solid statistical method to estimate selection coefficients. So now simply what we need is to fit this logistic curve and find the growth rate, which is the growth rate of this logistic curve, which is the selection coefficient. Yeah, sure.
What do you mean for frequency of the variant?
For what?
Frequency of the variant.
Frequency of the variant is actually the incidence of the new variant over the total incidence. So if we have two variants, is the incidence of the new variant and the resident variant. So yeah, okay.
Assume if one will eventually take over, will have less.
Yeah, we have to assume that there is exponential behavior. So either both of the variant are exponentially grows. So this equation actually validates at the earliest stage of emergence. And this is the case that we are looking for, because we want to know, if we refer at this part, we want to know that what happens when a new variant emerges at the first few weeks. So if the new variant is able to be dominant, and what is the speed of this getting dominant? Okay, so
It takes over the population, right? There's a point where it's only one, or you don't have one or one and then have to have one.
Okay, the question was that when we mean dominant, does that mean that the frequency reaches to 100%, right? Well, that is the case. Fortunately, in most cases during COVID-19 pandemic, that was the case. So when we had a new VOC, variants of concern, that completely don't get dominance and replace the old variant. But in some cases, we may face coexisting phases, which means that two variants can coexist with each other. In those cases, what we really care about is this growth rate at earliest stage of the emergence. So still we can assign a growth rate. Of course, it wouldn't be assigned to the whole period, but for the few weeks of emergence, we can assume that the new variant has a exponential growth. So this equation can be valid for a few weeks, but after a while, you may not see this nice logistic curve, and then they saturate at a lower level, like 80%. But that is not the case at least in our studies, because we study on alpha, delta, and omicron, and those variants gets dominant.
Assuming independence in the interaction between variants. So because if they are not independent, it's not obvious that you will have an exponential growth in both of them.
Yeah, that's true. That's true, but okay, that's true. But if you look up, okay, the question was that. Okay, can you rephrase the question?
I'm just saying that I think you're assuming independence in the interaction between variants. So you're not taking into account that they interact at all, because you're assuming that both of them are exponential.
Okay, the question was that as we assume that both the growth rate are exponentially, this means that we are not assuming that the two variants are interacting with each other. Well, no, that's not the case. Because I will explain how this interaction can be modeled. So even if we have interaction, the interaction depends on the level of immunity. So if we assume that the new variant emerge when there is a higher level of immunity, that means that there is already a lot of people who are infected. So that empower the interaction term, but also that depends on how these two variants can interact. For example, for alpha variant, we know that there is almost fully cross immunity. That means that if you get infected by the previous variant, it's not possible, it's near to impossible to get infected by the new variant. But in other variants, such as Omicron, we know there is a partial immunity. So in those cases, still the new variant can propagate because there is a chance of getting infected. And yes, our main aim in this study is how this selection coefficient depends on these interaction terms. So I'm gonna refer to that shortly. So the key factors that interfere here are first immunity level, then cross immunity, then the transmissibility of the second variant, and also the structure of network. This is actually the topic that I'm going to present. So here I compute the selection coefficient for three variants, Alpha, Delta, and Omicron, across different US states. So each point here is a state in United States. So we can see that, first of all, we can see that Omicron has a higher selection coefficient. This is due to the immunity evasion that Omicron has. But interestingly, we observe that this selection coefficient has a variation, has a significant variation across different regions. So the question is, what are the source of this variation? Because we are talking about a given variant. Basically, many factors can affect. Obviously, the phenotypic properties of the variant, like immunity evasion, increased transmissibility, and etc. But also other factors like immunity level, like the different surveillance system, the intervention that government had done, and population characteristics like the age and other mixing patterns can also affect. But as I mentioned earlier, there are extensive number of studies that suggest that network structure can affect also the co-circulation and interaction between two variants. So this means that in principle, network structure can affect the selection coefficient, the advantage of a virus. And let's see if it can explain at least a portion of this diversity or not. So our question is that, okay, assuming a structure, a network structure, how we can model the behavior of selection coefficient with respect to the structure of network. And does this model explains this diversity, this geographical diversity or not? So to address this question, we came up with a computational model our model consists of two parts. In the first part, we assume we build a network structure, and then we consider we model the co-circulation of two variants using the SIR model. Okay, to construct our network structure, thank you. We consider a two-layer network to be more realistic. The first layer represents interaction or contacts outside the household, so we call it social layer. We use configuration model with negative binomial to create this social layer. Then at the second layer, we consider the interaction inside household. So for this layer, we consider fully connected clique. So we assume that within each household, everybody connects to everybody. And then we assume a zero truncated Poisson distribution for the household size. Okay, considering these two layers, what we really care about here is two parameters of our constructed network. The first is the density of the links, so mean degree. And the second important parameter is the variation in degree. So we can parameterize that as a coefficient of variation, CV, which is a standard deviation of degree over mean degree. So this term actually represents the heterogeneity in our network. Higher CV corresponds to a heterogeneous network, which the existence of hubs are quite frequent. Lower CV corresponds to homogeneous structure. Then we simulate, then we use a SIR model, susceptible, infectious, recovered model to simulate the spreading of a single disease. So initially we let the resident variant spread through the network. Then at a specific time when the cumulative incidence reaches to a certain threshold, we introduce the second variant. At this point, actually we have a two variant SIR model. So these two variants interact with each other through the cross immunity. Cross immunity is the amount of immunity individuals can gain if they have been previously infected by the other variant. So 0 means that there is full cross immunity, so there is no possibility to reinfect. 1 is no immunity. So if sigma, our cross immunity is 1, that means that the two variants has no cross immunity. So if you get infected by 1, you can easily get infected by the other. Well, the main important parameter here is the immunity level that I tagged. So this is the cumulative incidence when we introduce the second variant. So it's immunity level, we call it immunity level at the time of emergence, or simply immunity level. And now let's move on to the main result. So as I said, we have 3 main parameters: mean degree, MD, coefficient of variation, CV, immunity level, IM. And 2 other parameters regarding the characteristic of the virus: transmissibility and immunity evasion. Well, to make it a little simpler to present the result, we consider 3 different scenarios. In first scenario, the new variant has increased transmissibility, but has no immunity evasion. This is more or less like alpha variant. In alpha variant was a more transmissible variant, but has no ability to reinfect. So we call it alpha-like scenario. The second scenario is where the new variant has the same transmissibility, but it has the ability to reinfect. And the third scenario is when the new variant has both advantage. So increased transmissibility and immunity evasion. This is this is actually more similar to the Omicron case during COVID-19 pandemic. So we call it Omicron-like scenario.
Your immunity evasion is not directional, it's the same, it's symmetric.
It's symmetric, yes. I may consider one little thing that I haven't showed here. Even if we have full immunity, and even if we don't have any immunity evasion, like alpha-like scenario, this means that one can be infected by both variants. But still, there is an interaction term, and that is because individuals cannot get infected with two variants at the same time. So even for alpha-like scenario, there is some sort of interaction because one cannot get infected by both variants at the same time. Okay. Sorry. Okay. Here I illustrated the result. On y-axis is selection coefficient, and on x-axis is CV, coefficient of variation. So in second scenario and third scenario, Omicron-like scenario, what we observed was that selection coefficient increases with coefficient of variation, with CV. This means that, well, as higher CV corresponds to more heterogeneous structure, this means that heterogeneity favors variants with the ability to infect, so favors variants that are like Omicron. Here the different thickness of the line corresponds to different level of immunity. As you can see that the selection coefficient also increases with immunity, but the effect of immunity fades out when it goes higher. So, for example, here you can see when immunity level goes higher than 15%, the lines gets close to each other, which means that the effect fades out. But let's see what happens in the first scenario. In alpha-like scenario, we observe the opposite behavior. So the selection coefficient decreases with CV and also decreases with immunity level. This means that more homogeneous structure favors a variant with no ability to reinfect. So in alpha-like scenario, we would expect that alpha variant would have much higher selection coefficient or advantage in a society that has a homogeneous contact structure.
That initial moment, the insertion of the second variant, right?
Yes, and that is the immunity level. We can reparameterize the time by the level of immunity that we introduce the second variant. Okay, so yeah, at a lower level of immunity level means that the new variant emerged earlier, but at a higher level. So this is just a reparameterization of time.
There is just for the second and third scenarios. Or
no. For both scenarios, we have this effect of immunity, but the effect is the opposite. For alpha-like scenario, the selection coefficient decreases with immunity, while for Omicron-like scenario, it increases with immunity. If you see here, the upper curve are thicker, which corresponds to a higher level of immunity.
okay, but I'm a bit confused. Maybe it's because I don't see really clearly the axis mediation in this view. But okay, the first you're showing the selection coefficient versus the heterogeneity of the network
Yes,
for the first scenario.
yes,
Sure. In the second plot, you are looking at exactly the same thing for the second and third scenario.
yeah,
And in the third plot, you're looking at the invasion coefficient versus
this one,
yes.
this is the same. Selection coefficient versus CV, heterogeneity for the third scenario.
The invasion thing is for the different curves. For the different lines in each of your curves.
Okay.
Yeah.
Look, if in this scenario, the cross immunity is 0. In these two scenarios, the cross immunity is equal and it is 0.6. The difference is that in second scenario, we don't have increased transmissibility, but in third scenario, we have increased transmissibility.
Just concerned about the invasion coefficient that you define. And it's each of the different curves.
Invasion coefficient, what do you mean by
the immunity coefficient.
immunity level?
Yeah,
Okay. Sure.
But so the different plots are for different, the different
Yes.
lines are for different immunity levels.
Yeah.
You're starting from which I don't see.
We start from 0 to 50%, but here I illustrated from 5% to 20%. For not get a very complicated graph, but yeah. So this is a parameter that we can change because this is our, decision to.
What you're saying is that even if the second variant start almost at the same time that the first variant and has higher infectiousness, but the sigma parameter is 0, but it's measured.
Mhm.
The first variant will.
Yeah.
I don't understand.
Yeah. The thing that you're referring is actually the case when immunity level is very close to 0.
Sure.
Okay. So I didn't, I should have plotted that too, but if when immunity level is exactly 0, so the both variant measure at the same time, this is a flat line.
So the second variant doesn't win,
No.
even though it's higher infectiousness. Because in your first scenario, you have higher infectiousness for the second variant.
Yes, yeah. Okay, no, I meant that, yeah, you're right. In this scenario, because we have increased transmissibility, that has a non-zero selection coefficient, because yes, the second variant has still a higher transmissibility, but we can consider a scenario which the transmissibility is as the same as the second one. So in that would be a flat curve. But here, yes, as we go on higher level of immunity, this effect would increase. So, okay.
What is the size of the network you're considering?
Well, here I am showing the result for 10K nodes, but I have done the size, the effect of size, some analysis on the effect of size, and in those analyses we consider from 1,000 to 1 million. For sure, for 1 million, because there are a lot of simulations, we cannot do it for every possible scenario, but we were convinced that the behavior is preserved. So here I illustrated again I'm sorry. The selection coefficient as a function of mean degree this time. For the second and third scenario, we can see the selection coefficient increases with mean degree or the density of network. But for the first scenario, actually, there is no, the trend depends on the value of CV and immunity. So it's not it doesn't have a it doesn't have a, a smooth curve, a smooth behavior. So I will come back to this later when I refer to empirical analysis, because now it seems that, okay, mean degree means that has a complicated behavior, but this complicated behavior manifests itself somehow in our data, empirical data analysis. Okay, let's see what is the intuition behind this effect of heterogeneity. Here I illustrated the two scenarios where alpha-like and omicron-like in the same plot. I just removed the y-axis, the scale of y-axis to, for the sake of comparison. Well, the effect of heterogeneity can be explained by the role of hops as super spreader or super blocker. So on the right panel, I am showing the network with almost heterogeneous structure. So in heterogeneous structure, the presence of hubs are quite frequent, and because hubs are the nodes with the most centrality, this means that they get infected quicker, and then they pump the infectious to its through its connection. So in this situation, when hubs get infected, they block plenty possible passes through which the infection can spread. This means that in this scenario, if a new variant have ability to have immunity evasion, it has the ability to infect the hub. So this means that the new variant can use the hubs and infect them to spread. So heterogeneity favors a variant with immunity evasion. On the other hand, in a more homogeneous structure, the nodes have more or less the same number of contacts. This means that if a node gets infected, there are still plenty other alternative passes which the variant can take it to spread. So this means that regardless of whether the new variant has ability to reinfect, what really matters is how fast the new variant can spread. So it means that it means how high is the transmissibility of the new variant. So in a more homogeneous structure, the network favors a variant with higher transmissibility. Okay, these simulation results shows us that, first of all, the structure of network plays a major role. Then dispersion in degree distribution favors a variant with immunity evasion. But also this variation, because we see that the selection coefficient varies significantly with CV, this means that this variation in selection coefficient that I showed you in the first plots can be explained by the heterogeneity of the contact network. So let's see if we can validate our finding with some empirical data analysis. Well, okay, here, as I said before, we have three main parameters: mean degree, CV, and immunity level. And we have the selection coefficient. So we want to model selection, empirically model the selection coefficient as a function of mean degree, CV, and immunity level. So this is not a simulation. I'm just talking about real data if we can find any. So to do that, we need three pieces of data: empirical selection coefficient, contact data, and immunity level. Well, empirical selection coefficient was, I showed you earlier. This is, okay, yes. Here, as I said before, we can compute the selection coefficient based on the incidence of the variant. So we did that for alpha, delta, and Omicron variant. And we're going to focus on alpha variant because due to, I will explain later, but shortly, because the contact network that we have is restricted to the alpha period. So let's focus on alpha variant. So we compute the selection coefficient of alpha variant across different states in US. Then we need to estimate immunity level. Well, immunity level consists. Okay. Selection coefficient of this variant with respect to the previous variant. Well, yeah, selection coefficient for one variant doesn't mean anything. Yes, so for alpha is with respect to the historical variant. Okay, well, the next step is to estimate immunity level. We assume that immunity level consists of two parts, natural immunity and immunity due to vaccination. Natural immunity can be estimated with seroprevalence data. And for vaccination, we consider two types of immunity as well. Partial immunity due to the people who have only received one dose of vaccination, and full immunity for those who completed their vaccination. So with combining this source of data, we can estimate the effective immunity level. So this is the time series of vaccination coverage and seroprevalence immunity. Okay, contact data. Finally, we use survey data on the number of contact individuals have during the course of alpha variant in different states in US. With this survey data, we could compute the average number of individuals contact, which in our model represent the mean degree, and its variation in terms of coefficient of variation, or CV. So this is the time series of mean degree for each state. So each line is a specific state, and the blue line is the average over the whole country. Okay, this is our model. We use a regression model to regress selection coefficient as a function of CV, MD, and immunity. So what we want to see in a logarithmic scale, what we want to see is the sign or the value of this coefficient to see what is the dependency between CV, MD, and immunity with respect to selection coefficient. So the result was actually promising. For CV, we find a statistically negative coefficient. This means that selection coefficient is negatively associated with CV. This is totally in line with our finding in simulations. This means that selection coefficient is higher selection coefficient is higher because it is negative. The selection coefficient is higher in states with a lower heterogeneity, because this coefficient is negative. But for MD, we find a weak negative association, and it is weak because the confidence interval is quite wide. And this is, again, I think is consistent with our result, because as I said, we couldn't find any monotonous behavior in terms of mean degree. That depends on the level of immunity and MD, and we know in real data, each state have its own immunity and mean degree. So for some groups of states, we may have a positive value, or for the other may have negative value. So overall, we have a big negative, but with a higher confidence interval. And then for immunity level, we find no association. This is also consistent with our result, because as I showed, the effect of immunity fades out at a high level of immunity. And we know at the time that alpha variant emerged, the immunity level was more than 10%. So that considered high. Well, that's it. Let's conclude. So my main conclusion is that, first of all, the structure of contact network play a major role in the growth rate of a new emerging variant. Then this structure can explain the diversity, spatial diversity that we observe across different regions. In an example, I present the diversity across different states in the US. And then our simulation shows that heterogeneity would favor a variant with ability to reinfect, while homogeneity favors a variant with increased transmissibility. And we could find an empirical validation for case of alpha variant. This is where homogeneity favors a more transmissibility, a variant with more transmissibility. Unfortunately, we cannot do much thing about the Omicron live scenario, because we don't have any direct data about the contact network. Maybe we can come up with some proxy. This is under consideration, but so far we have this conclusion. Then our study provides insight that can inform public health strategy to design intervention and managing the co-circulation of variant of concern. But also we suggest, our study suggests that contact network, is a key factor for explaining the spatial variation in estimation of characteristic of a variant. This means that it could be potentially a source of bias in our estimation. I mean that if we estimate let's say the increased reproductive number of variants in UK, we should be aware that we cannot generalize that to elsewhere, because we know that there is a spatial diversity. Well, thank you for your attention. And at the end, I would like to acknowledge the other co-author. Chiara is my supervisor. She's right now at the Padova University. Then the rest are Elisabetta, Lula, Shuta Banzal, and Juliana. And I would like to thank them also, as well. Thank you for your consideration.